After being discussing about the two of the colligative property, the one is relative lowering in vapor pressure, and the another one was elevation in boiling point. Now moving towards the third colligative property, that is depression in freezing point. So before discussing about this depression in freezing point, firstly we will know what we call freezing point and what this freezing point is. As we all know that freezing is conversion of liquid state into solid state. Freezing is what? It is conversion of anything from liquid state to solid state. And freezing point, this freezing point is actually a temperature at which this liquid and solid state exist in equilibrium with each other. When at particular temperature this liquid state and the solid state are in equilibrium with each other, then that particular temperature would be considered as the freezing point. Liquid state is in equilibrium with solid state. So the temperature at which the liquid state will be in equilibrium with the solid state, then that particular temperature will be considered as freezing point. Here equilibrium means the conversion of liquid into solid would be equal to solid into liquid. The rate at which liquid is converting into solid will be same as the rate at which this solid would be converting into liquid. We can define this freezing point in one more manner also, and that is when at any temperature the liquid state and solid state both have the same vapor pressure, then we can call that temperature as freezing point. So one more manner to define this freezing point is when liquid state and solid state has same vapor pressure. So at that particular temperature, when the liquid state and solid state are at the same vapor pressure, then that particular temperature would be considered as the freezing point. Now let's move further. For this, let's consider a container. Suppose this container is containing a pure solvent. Here pure solvent is present. Now this pure solvent has some particular vapor pressure. Some vapor would be formed over the surface of the solvent, and due to which there would be some vapor pressure. Now what happened, we added some non-volatile solute in it, in the same container which is containing the pure solvent. We added some of the non-volatile solute. As the non-volatile solute is added, now what will happen, we all know from previous videos we have been seeing that as the non-volatile solute is added, due to addition of this non-volatile solute, vapor pressure would decrease. Vapor pressure will become less than that which would be present over here, and now vapor pressure is decreased, vapor pressure became less. This vapor pressure which is lowered, it is because of addition of this non volatile solute. इस नन वोलेटाइल सॉल्यूट के ऐड होने के कारण यहाँ पर वेपर प्रेशर क्या हो गया, घट गया, कम हो गया. प्योर सॉल्वेंट का जो भी वेपर प्रेशर होगा उसके रिस्पेक्ट में जब हम सॉल्वेंट के अंदर नॉन वोलेटाइल सॉल्यूट ऐड करेंगे तो वेपर प्रेशर जो है वो लेस होगा, लोअर होगा. ये हम शुरू से ही देखते आ रहे हैं. नाउ अब बात आती है फ्रीज करने की. लेट सपोज वी आर गोइंग टू फ्रीज दिस प्योर सॉल्वेंट. वी आर गोइंग टू freeze it and convert it into the solid state. In the same manner, we have to freeze this also, this solution in which pure solvent is being mixed with non-volatile solute. We have to freeze it also. Both are to be freezed, and for that a particular temperature must be attained, a particular temperature at which both of them will convert from their liquid state to solid state. Now if we will apply Raoult's law over here, due to addition of non-volatile solute, the vapor pressure has decreased. As the vapor pressure has decreased, now when we will take both of them to the freezer, or we will try to freeze both of them, we will observe that this pure solvent will freeze at higher temperature in comparison with this solution. It means solution will convert into a solid state at lesser temperature. It means we can say over here freezing point will be lesser, will be decreased in comparison to this uh, pure solvent. So in simple manner we can say that when some non-volatile solute is added in the pure solvent, there will be a decrease in vapor pressure, and due to decrease in vapor pressure, the freezing point of the solution will be less than the freezing point of the pure solvent. The final conclusion is only this, that freezing point of solution will be lesser than freezing point of pure solvent, and mm, this happens because of the addition of non-volatile solute. So let's suppose that Tf naught is the freezing point of pure solvent, and this Tf is freezing point of solution. So according to our discussion, we can say that Tf naught means the freezing point of pure solvent will be greater than Tf, meaning freezing point of the solution. Now we will find the difference in between this freezing point. So Tf naught minus Tf, represented as delta Tf. This delta Tf is nothing. This is what we call as depression in freezing point. This is depression in freezing point which occurred due to addition of non-volatile solute in the pure solvent. This depression in freezing point is now being related with lowering in the vapor pressure, and in the same manner as we have discussed in elevation of boiling point, in the same manner we will go through depression in freezing point also. So this delta Tf is directly proportional to what? To lowering in vapor pressure, yani delta P we can say. And we all know that this delta P is also directly proportional to Nb by Na, where Nb is the mole of solute while Na is the mole of solvent. Now for a dilute solution, if our solution is dilute, then for that delta Tf will be directly proportional to M. What is this M over here? Again, this M is molality. This is molality of solution. Delta Tf, we will remove this proportionality sign with the sign of equal, and here will come a constant Kf into M. And what this Kf is, this Kf is a constant known as molar depression constant, or we can also tell it as karyoscopic constant. Now we will bring about some changes in the expression. Delta TF is equal to Kf into M, and as this M is molality, and if in the starting lecture, if you are remembering all that concentration term, where we have talked about molality, molarity, normality, mole fractions, and many others, from there we got that molality is what? Mole of solute by mass of solvent in kg. So we will put that expression for molality over here. We will change it, so we can write molarity as mole of solute by mass of solvent kg. This came in place of this m, molality. In place of this m we have put this term. Now I am going to convert it in the symbolic form. Delta TF is equal to Kf into mole of solute. What is this mole? Mole is given mass by molecular mass. So given mass of solute, it would be written as WB by molecular mass of solute, MB by mass of solvent in kg, mass of solvent Ma, and for kg divided by 1000. Delta TF is equal to Kf into WB by MB into 1000 by Ma. This WB, here WB is equal to given mass of solute, MB is equal to molar mass of solute, and this Ma mass of solvent. So the final expression for TF would become like this. TF is equal to Kf into WB into 1000 by MB into Ma. And here once again I am telling this Kf is what? This is a constant known as molar depletion constant or karyoscopic constant. This is the what we have to see in depression in freezing point. This expression can also be used to calculate the molar mass of the solute, and for that we have to, if we need to calculate this molar mass of solute, then we will send all this term to the another side. So that depend upon the question, condition of questions, that what we need to find. If we need to find this WB, so we will send all this term to that side and we can get WB also from this expression. Now lastly, Kf, which is molar depression constant, and Kb, which is molar elevation constant. In the case of elevation boiling point, this constant term came, and in the case of depression in freezing point, this constant term came. So both of these constant term depend upon nature of solvent. If we have to change the value of Kf and Kb, then it can only be changed because of the nature of solvent. The solvent nature only decides whether the value of this Kf and Kb will remain same or it would change. The last expression which we have to keep direct in our mind is of Kf. This Kf is equal to R into M into TF square by 1000 into delta H of fusion. Here this R stands for gas constant. This R is gas constant. This M stand for molar mass of solvent. M is molar mass of solvent. This TF is equal to freezing point of solvent. fusing point of solvent means pure solvent. Delta H fusion, this is equal to enthalpy of fusion. Enthalpy of fusion of solvent. So these are some of the terms which are used in the expression by which we can find the value of Kf. In the same manner, it would be for Kb also. For Kb, all the term would remain same, but instead of this delta H fusion, it will become delta H vaporization, because simply in case of boiling, here the fusion term will change. Enthalpy of fusion will become enthalpy of vaporization, and all the other term will remain same. So this is all we have to see in the definition of freezing point. The third colligative property, the important thing which we have to keep in mind is the this expression. Firstly, that delta Tf will be equal to Kf into m, and the next expression which this m molality is being converted into mole of solute by mass of solvent in kg, and the final expression which is obtained is this one. And the next we have to keep in mind is that this Kf and Kb depends upon the nature of solvent, and we can calculate this Kf by using this expression. For Kb also same kind of expression is present, but instead of delta H of fusion means enthalpy of fusion, enthalpy of vaporization term will be used. So that's all for this depression in freezing point. And in the next video we will see the last colligative property, and that is osmotic pressure.